So what lies ahead for telescopes? Well, we've updated Galileo's design. That's a nice thing that happened during the International Year of Astronomy in 2009, which was celebrating 4 centuries since Galileo's first use of the telescope. This year saw the launch of the Galileoscope, which was a version of his best instrument made with modern materials. And because it'd be mass-produced with cheap plastic, it was actually better than his best instrument, and the initial version only cost $25, including the tripod. And you actually do need a tripod if you buy this telescope, because holding it with your hands, it's impossible, since the field of view is so small, to keep an object in the viewfinder. So highly recommended with any telescope of this kind of design to get a tripod. Here's the history of optical telescopes since Galileo. At the left, you can see that Galileo's telescope improved sensitivity over the naked eye by a factor of 100, close to 100, by the end of his telescope making. That's pretty impressive. But what you can also see is incredible gains since then. And with the best images made with the Hubble Space Telescope, reading the logarithmic scale on the left, you can see that we now have telescopes that can do 10 or 20 billion times fainter than the naked eye can see. That's an incredible gain in sensitivity. We also now have a dozen or more 8 or 10 meter telescopes, with even larger telescopes to come. So we're in a golden age of optical astronomy, but it did all start with Galileo. In resolving power, or minimum angular resolution, the gain is not quite as dramatic, because that goes as the linear size of the telescope rather than the square of the size with collecting area. So we can see the minimum resolution in arc seconds, and the human eye with 1 arc minute, as we see, 60 arc seconds. Galileo's best telescope brought that down to 3 arc seconds. A major ground-based observatory in the middle of the last century would be about an arc second, and the Hubble Space Telescope takes that down to 5/100ths of an arc second. So that gain in resolving power of 4 orders of magnitude is a lot less than the 9 or 10 orders of magnitude of depth of vision, but it's also quite dramatic. What does 10 billion times fainter than the eye look like? Here we see the deepest image of the sky ever made using the Hubble Space Telescope. Here are some of the telescopes that are waiting for us in the future. The one I'm, of course, most excited about is the one that we're building here. Rather, we're building it in Chile, but the mirrors are being made here. It's an international collaboration involving other universities and other countries. If you look down in the lower left in this mock-up, you can see a human for scale. The vastness of this telescope is truly amazing. 22.5 meter, the giant Magellan telescope. The Californians and Caltech are planning a 30-meter telescope, and you can see it here superimposed on the buildings of Parliament. Canada is one of the partners, to give a sense of the scale of this incredible facility. What does 30 meters buy for you? Here's an animation which shows the best you can do without any adaptive optics, and you'll see a big blurred image. That's from ground. Now we go to Keck 10-meter telescope with adaptive optics, and then we go to a 30-meter extremely large telescope with adaptive optics. It's worth looking at this one more time because we're seeing an animated view. These are objects towards the center of our galaxies, and these are individual star motions that could be mapped over time to weigh the black hole in our galactic center. The more stars you can use to measure their orbits, the better data you get on the black hole. With adaptive optics in the Keck, what's currently possible, you can see how many orbits, maybe a handful. With a 30-meter telescope and adaptive optics, you can increase the number of orbits dramatically. So in this one experiment of measuring the mass of a black hole, adaptive optics has an incredible effect. The overwhelmingly large telescope that the Europeans originally conceived of as 100 meters has been descoped to about 40 meters, and it will probably be built in Chile in the next 5 to 10 years. At the level of 100 meters, you can see the comparison to one of the greatest constructions in human history, the Great Pyramid of Giza. These are incredible engineering achievements. To have a giant object like this of tens of thousands of tons move with a precision of 1 part in 10 to the 8 into an angle on the sky in real time, that's an amazing thought. What does 100 meters buy you? Well, obviously, a lot. Here's the adaptive optics in sequence from the ground, Hubble Space Telescope, 8 meter from the ground, and the 100-meter telescope. So dramatic gains are caused by adaptive optics and bigger light-gathering power. We can visualize the Giant Magellan Telescope as it will be built. The mountain has been scraped off, most of the mirrors have been cast, and it's only a few years from taking its first light. In that video, you could see lasers beaming off into the sky. That's actually the mechanism by which the adaptive optics works. Sodium lasers are shone off the upper atmospheric layer where the turbulence is occurring, and that reflected light is brought back to a reference system which shows how the path length of waves of light is being changed by the turbulent motion. That's fed into a closed-loop system, iterated, and that feeds into the sensors that change the shape of the secondary. And this is all done 10, 20, or 30 times a second to account for the rapid turbulent motion. This is high technology brought to bear on making sharper images. Here are the ways of seeing the universe and how they've changed, some of which we've yet to talk about. For most of the history of humanity, it was naked eye astronomy, and everyone got to see the same thing. The skies, of course, were dark before civilization, so everyone had a dark night sky when the moon was not around. In 1600, Galileo invents the telescope and expands our vision by orders of magnitude. And the progression of telescopes since then has just been to gain in light-gathering power by factors of millions and then billions. Two other revolutions in the ways of seeing the universe came in the 20th century. The first, over a period of decades, was the development of technologies to make images and detect waves of light not in the visible part of the spectrum. That opens up the electromagnetic spectrum all the way from radio waves to gamma rays. Those very short waves have to be viewed from space because they don't come through the atmosphere. But the detectors to detect radiation, electromagnetic radiation over a range of 1 trillion in wavelength, from meter-length radio waves to gamma rays that are smaller than a proton, is available. We can observe the universe in all these waves of light. And in the early part of this century, another revolution occurred when we first detected gravity waves. And we've learned with gravity wave detectors how to see the universe with gravity eyes. And that's the end of this module.